Hi, I'm Professor Harry Porter. In this video, I'm going to be showing you some very clever C code that's well worth studying in detail. As a C programmer, you're probably familiar with the Malloc and free functions that we'll be looking at. The C language reference book by Kernighan and Ritchie gives a very clever implementation of Malloc and free that's both short and sweet. It's a good example of C, and I'll be describing the algorithm and walking you through the code in this video.
You probably remember that malloc is called to get a chunk of free memory. You pass malloc a single argument, that is the number of bytes you want to allocate, and it returns a pointer to a block of free memory of that size. Later, you can call the free function, passing it that same pointer, to return that memory to the free pool. To write correct code, we need to be very precise about edge cases. For example, we must say exactly which argument values are legal and whether the error conditions will be checked by the calling code or by the code in the malloc and free functions. Of course, the free function must be passed a pointer that was previously returned from malloc, and each block of memory may only be freed once and must not be accessed again after that. We say must to mean that malloc and free will likely fail if the caller doesn't respect these constraints. We can also add that the memory address returned by malloc will have the most general alignment as appropriate for whichever system you're running on. And malloc will return the null pointer, that is 0, if it's out of memory and can't satisfy the request. The code we'll be looking at is exactly the code from the Kernighan and Ritchie book. Modern Linux systems use more complex algorithms to implement the same malloc and free functionality, but the simple implementation here works just fine, at least for single-threaded applications. This implementation will invoke the sbreak system call to request blocks of memory from the kernel. Here's a general diagram of a process's address space. We see the area containing the code and data in low memory and the stack in high memory, and we have a heap which is growing upward. The kernel maintains the break address, which marks the top of the heap. sbreak is used to enlarge the heap, incrementing the break address and returning the previous value, which is the address of the chunk of memory that's being allocated. Malloc will periodically invoke the sbreak system call to get an additional large chunk of new heap space from the kernel, which it will then use to satisfy a bunch of individual requests. The chunks of heap used by malloc need not be contiguous if other code is also calling sbreak. By the way, sbreak is now considered obsolete and shouldn't be used. User code would normally invoke malloc or calloc directly, and the modern implementations of malloc would call mmap or munmap to get and return heap space from the kernel. But let's ignore that inconvenient fact so that we can explore this algorithm. The malloc and free code will maintain a free list of memory blocks. All blocks of memory, whether free or allocated, will contain a header, and the header will contain a pointer and a size. The header will be hidden to the user code. The address returned to the caller will be just beyond the header. So if n bytes are requested, the block will actually have a size of n plus the size of the header, although the user will only access and use the bytes that come after the header. The blocks on the free list are joined in a circular linked list. For blocks that have already been allocated, the pointer field is just not used. We can also say that we never have two free blocks that are exactly adjacent and touching. To prevent this situation, every newly freed block will be merged if there's another adjacent free block either directly before or after it. The free blocks will be kept in order, that is, in the order they occur in memory. So all next pointers will point to larger addresses, with the exception of the final block's pointer, which points back to the lowest block. We need to keep them in order so that we can check whether or not to merge a block with the previous block or with the following block if they are contiguous. Now every block, whether allocated or free, will have a size field. One clever thing about this code is that it doesn't work in terms of bytes, but in terms of units. The size of a unit is exactly the size of the header. Every block has a size that is an exact multiple of units. For every call, Malloc will round up the requested byte count to a multiple of the unit size. For example, this chunk has size 3, 1 for the header, and 2 which contain at least as many bytes as originally requested. So we're really working with a sequence of units where every unit is the size of a header. Also, every unit will be properly aligned, which assures that any address returned by Malloc will also be aligned, as is required. For each request, Malloc will search the free list for the next free block that's large enough. If it's larger, then it will be split into 2 pieces, leaving the remainder on the free list for future use. More precisely, we'll split off a few units from the tail end of the free block to satisfy the allocation. We'll leave the free block itself, or what remains of it, on the list, so no linking or delinking is necessary. We just need to reduce the size of the free block by however many units we cut off of the end of it. By using units, it means that whenever we split a free block like this, we can be assured that the remaining free piece will have at least 1 unit, that is enough space for a header. Now, in the extreme, so-called degenerate case, it may have no additional units beyond that header. Note that if there's ever a request for an allocation of size 0, such a degenerate block could actually be used to satisfy it. In fact, degenerate requests for 0 bytes are handled just fine, with no code required for special case checking. When we allocate a block, we may need to remove and delink it from the free list. Whenever a block is freed, it must be added and linked back into the free list. We use a circular linked list, which means that we never have to do any special casing to deal with the front end or the tail end of the list because it's a circle and there is no end. To make all this work, the list must always contain at least 1 element, so we'll need a so-called dummy block. The minimum block size is 1 unit, which is for the block's header. This dummy block will be given a size of 0, which means it's too small to ever be usable and allocated, even for that degenerate case where the requested byte count was 0. We've also got a variable called free p, which points to one of the blocks in the circle. This is the free list pointer. Whenever we have to search for a free block, we start wherever free p points. After finding a free block and doing that allocation, we leave free p at that point so that next time we start searching wherever we left off last time. This is sometimes called a next fit search, as opposed to a first fit or a best fit search. During a search for a free block, if we go all around the circular list and come back to where we started, we know that there is no free block that's large enough. That's going to trigger a call to sbreak, which will add a new free block to the list. Then we search again and immediately encounter this newly added free block, so the request can then be satisfied. We'll initialize everything in the first call to Malloc by creating a list with only the dummy block. That first call will find no free blocks large enough, since there are no blocks at all beyond our dummy block, and that will trigger a call to sbreak to get a new heap chunk, which will then be turned into a giant free block and added to the list. Then the allocation is reattempted, and this time it would succeed. Note that aside from creating the initial dummy block, there's nothing else in the initial Malloc code that is a special case, and I think that's really clever and clean. Here's the code itself. It begins with comments, includes, and a # define, which we'll skip past for now. Then we get to the definition of a type called header. Here you see a structure with two fields, a pointer and a size. This structure is wrapped inside a union, and the union has two variants, S and X, which will be overlaid and will occupy the same memory bytes. X is of type align, which we equated here with whichever type has the most restrictive alignment requirements for this code and the system we're demonstrating. Apparently, that's just a long integer. The point of this union is to make sure that all headers are aligned on the most restrictive boundary. Other than forcing alignment, this X variant is never otherwise used. However, every time we access the pointer or the size field, we'll need to qualify it by also specifying the S variant of the union. Next, we have a type def, so from here on we can just write header with a capital H instead of writing union header. Then we see something called base. This is the dummy list element, so it's a header structure not followed by any data bytes. Then we see the free p variable, which is a pointer to headers. C guarantees that global variables such as these will be initialized to 0, and later we'll use the fact that free p is null to detect the uninitialized state. The static keyword, when used for global variables like these, simply restricts their visibility to just this one .c file. Now let's look at the Malloc function, which is passed a byte count. The code uses unsigned, meaning an unsigned integer, but you might prefer to use something more specific like uint64_t. Arithmetic overflow, which this code assumes will never happen, must be considered if security and malware are issues. The function returns a pointer, and of course a void pointer will match any other pointer type, so no typecasting will be needed in the calling code. We've got a couple of pointers and a count of the number of units we'll need to allocate. The first step is to turn the byte count into a number of units. So first we divide the byte count by the size of a header. Integer division will of course truncate, rounding down, but we want to round up. This pattern, where we first add one less than the size of the header before we do the division, will achieve that rounding. Then we add one more for the header itself, in addition to the units that will contain the region of the data bytes to be returned. This if will test to see if free p is null and do the initialization, if so. This code uses 0 instead of null, and this is a stylistic decision. It's perfectly legal. I guess, how do you feel about this choice? Ignore the assignment for just a moment. This code initializes the base element, that is, the dummy list element. The size is initialized to 0, and the pointer is initialized to point to the dummy element itself. We also initialize free p to point to the dummy list element. Then, regardless of whether we do it in the if condition or in the then part, we also set prev p to the same as free p. You can see how whenever we're looking at the pointer or size fields in a header unit, we have to add the s dot stuff because of this union. So from here on out, just ignore the s dots. Now we get to the loop. It'll move two pointers through the list, pointing to two successive elements. P will point to the element we're looking at, and prev p will point to the element directly before it. We need a pointer to the previous element in case we have to delink the p element. We begin by moving p to the element just after prev p. And then to advance, we move pre-p ahead to p, and then we move p to the following element. The for loop doesn't contain an exit condition. We can only get out of this loop by returning. We'll be looking at P to see if we can use it for the allocation. We'll start with the element just after the free P element. If we can't find anything, we'll eventually loop around the circle. If we find that the element we just looked at was the free P element itself, then we couldn't find a free element that would work, and this if statement gets triggered. So we'll call this helper function Morecore, passing it the number of units that we need. It will enlarge the heap and add a new free block just after free P. If for some reason it fails, we're out of memory, so we immediately return null. But otherwise, we iterate the loop one final time. At this point, P will point to the free P element, and then on the next iteration, P will point to this newly added free block, and the allocation will necessarily succeed. Now let's look at what happens here. P points to some element in the free list. Is it big enough to satisfy this request? Well, if it's exactly the right size, we delink it from the free list by modifying the next pointer of the previous element to point to whatever element follows P. Then we go down here. We modify free P so that the next search will start where this search left off. And we also return a pointer to the data area just beyond the header. Since our pointers are all pointers to headers of size unit, I guess, then incrementing it by 1 will cause it to return the address of the byte following the header. Since the function is declared to return a void pointer, the cast to void pointer here is not really necessary, but it could help clarify this code. Now, what if the object pointed to by P is larger than necessary? We're going to remove a few units from the end of this object to satisfy the request. So first, we reduce the size of P to whatever remainder we have. Then we need to compute a pointer to the second part of the block, to the newly created block. So we increment past the remainder. This gives us P pointing to the block that we're going to return. We need to initialize its header. We care only about its size field. Its pointer field is just left uninitialized. Before we look at the Morecore function, let's look at the free function. It's passed a pointer to a block of memory, AP. That is a void pointer, so it matches any kind of pointer. We immediately decrement it by the size of the header to get BP, which is a pointer to the header for the block that's getting freed, and then AP will never be used again. In this loop, we search the free list for where to insert this new block. Remember that blocks are kept in order according to their memory addresses, so we'll set P to point to the block directly before BP, and we'll insert BP directly after P. So we start searching at the beginning of the free list, free P, and on each iteration we move to the next block in the linked list. The loop terminates when the address of BP is greater than P but less than whatever block follows P. It's a circular list, so at some point it loops back to lower memory. This test detects this point by becoming true when the address of P is greater than the address of the block that is next in the linked list. If the block we are freeing, BP, is either after P, that is beyond the block with the largest address, or before the block, that is below the lowest block, then we need to stop and insert the block at this point in the linked list. In any case, after the loop, P points to a block and we'll insert BP after P. The first if is used to merge the new block with the block just after it if they're contiguous, that is, exactly adjacent in memory. The second if will merge the block with the previous block, which is P, if P and the new block are adjacent. If there is no merging needed, the else cases will be used. So just looking at the else cases, we first make the new block point to whichever block followed P. Then we make P point to the new block instead of whatever it used to point to. Now, if we're merging BP with the following block, it's BP's header that will serve as the header of the combined block. We start by combining their sizes. Then we make BP point to whichever the block getting absorbed previously pointed to. So whether we're merging or not, we're setting BP's next pointer to point to whatever should now follow BP. In the second if statement, we'll be updating P's next pointer. If we have to merge P with a new block, then P's header will serve for the combined block, and BP's header will become forgotten. So we begin by setting the size of the combined block. Now we've already made BP point to the remainder of the linked list. That's BP's pointer. Now we make the pointer of the new block point to whatever we'd previously decided would follow BP. Finally, in all cases, we update free P to point to P. We do this so that the next time we need some free space, we'll start the next search at this point. I think this is really tight code, and to fully understand it, you might want to pause the video right here and study it a bit. Okay, now let's look at the Morecore function. By the way, core is an archaic term for main memory. Remember that if we're looking for free space and we go all around the circle without finding a big enough region, we'll call Morecore. It's passed the number of units we need, and it will add a new free block somewhere in the free list. It'll return 0 if it fails, or it'll call sbreak and allocate a sufficiently large block. It'll return free P, which will point to some block from which we can resume searching. Malloc is a # define that gives the minimum amount to request to sbreak. We don't want to make a system call for every small allocation. That'd be too inefficient. Instead, for every call to sbreak, we want to grab a very large chunk, which will hopefully satisfy many small calls to Malloc. So we begin by rounding the request size up to Malloc if it's smaller. The request size, which is named NU, or number of units, is in terms of units, and in this code, Malloc was equated to 4K. So if our headers are, say, 2 double words or 16 bytes in total, that would mean that we'd be asking for 64 kilobytes each time. Then we call sbreak. If it fails, it'll return a special code, which happens to be -1. So here we're using a define constant, sbreak error, instead of simply saying -1. In the Kernighan and Ritchie book, they just said -1 instead of using a named constant. Which is preferable, using a named constant or the actual value? I'm not really sure what I'd recommend in this situation. But in any case, we return the null pointer if there's a problem so that Malloc can forward the error to the user code. Then we set this memory up with a header so it will look exactly like a block that Malloc previously allocated. We use HP, which is declared to point to a header structure, and we'll fill in the size, which is the number of units. Now it looks just like any other block, so we can call the free function to add it to the free list. Of course, free is normally called by the user passing a pointer to a data area, not to the header, so we'll need to increment HP by the size of the header before we call free. Free will add it to the free list, updating free P. Normally, the free function will end by setting free P to point to the block directly before the block it just added. This pointer will then be used in the continued search in Malloc, so P in Malloc will be set to point to the block directly before the block we just added. Malloc is capable of removing the next block after P. Recall that it needs a pointer to the previous block so it can do the delinking. So it will immediately be trying to remove the block that Morecore just added, which is perfect. Now, in rare cases, free may find that the newly allocated block is directly adjacent with the previous block. It'll then merge them, and this would cause it to set free P to point to the new block itself. Back in Malloc, P would not be pointing to the previous block, but directly to the new block. And that would force Malloc to go all the way around the free list circle a second time before it came to the element before the block where it could actually perform the allocation. But hey, what are you going to do? Okay, this is an amazingly tight and beautiful piece of code, I think, and I hope you've enjoyed walking through it with me. Don't forget to subscribe if you want YouTube to recommend more videos from me in the future. Well, let me end by saying I hope to see you in the next video, and thanks for watching.